Well, welcome everybody. Today we're gonna hear from Pete Baldwin, past president of Ramgen Power Systems. Pete is a global leader in the gas turbine and compressor industries, and in keeping with our evolving interest in power generation and the environment, Pete will speak on carbon capture sequestration uh, opportunities. So that's what he's going to talk about. But I want to mention before I turn the floor over to you, Pete, for the benefit of the rest of our crew, that earlier this year, Pete was recognized and received the 2024 Dedicated Service Award from the American Society of Mechanical Engineers, which is a really great honor. So, Pete, I'm delighted to have an award winner with us this morning. Yeah, I just have one question for you, though. I noted that the award was going to be presented at a meeting in London, so I have to ask, did you go to London to receive it, or
I am mobility challenged. I
oh,
know
okay.
London very well. We lived there for 2 years. I know you must be able to walk and walk quickly when you're in London, and
Hmm.
I just didn't think that I could handle it.
Okay.
And I'm very disappointed. It is one of my favorite places of all time.
Yes, I love the Agatha Christie shows that are always
Yeah,
available on
yeah,
stage. At
yeah.
any rate, Pete, welcome again. I'll turn the floor over to you. I see your presentation is up, so
Yep.
carry on.
So how did a nice guy like this get involved in carbon capture and find himself in the middle of these kinds of conversations? Uh, let's see if they'll actually, there, it doesn't look like it's moving, being recorded. Okay, so I was doing due diligence for venture capital in the energy tech because I was a microturbine guy coming out of Northern Research, doing independent consulting work, and I did an evaluation of Ramgen as a potential evaluation. At the time, Ramgen was trying to make a gas turbine, supersonic, with all of the components on the rim of a disk. And I expressed to the venture guys that this looked a little too risky, and so I said, "Hey, don't invest." Several years later, I ran across one of their uh, participants, and they said, "Well, they'd had a meeting with DOE and Rolls-Royce and NASA, and it was suggested that they concentrate on the compressor and the combustor." And so we reconnected, and I said to them, if you can make it work, I can tell you where you can sell it. And so what the technology is using the supersonic platforms, not unlike this F-15 inlet structure where you see the ramp-like structure, and this is a supersonic compressor. And so what Ramgen did is to take that compressor shape and put it on the rim of a disc, and then you turn the disc uh, with a motor, and you end up having a developed a compressor. And you can see this is Ramgen material, but you can see the attempt to generate and control the shock and use it to boost the pressure. We were funded by the Department of Energy and to develop the compressor technology, and you can see an artist's rendition of the ramp and the rotor, and of course we talked about it as a single stage compressor technology driven by electric motor, and we were able to talk about pressure ratios 10 to 1 on a single stage compressor, which was remarkably high in its day. And so we were in the midst of developing that, but it was for a pressure. It was for an air compressor, 10 to 1, which is a market that I knew quite well, having worked for Ingersoll-Rand for 25 years. So here we were on the effort to develop an air compressor. Then, quite by coincidence, I was invited to a DOE joint technical session with the Norwegian equivalent of the DOE. And I'm in a meeting having a cocktail after my presentation, and I meet this guy named Tore Torp. And he was the advisor to Statoil in Norway for CO2 storage. And he says to me, Pete, what you need is a pressure ratio of 100 on CO2. And I had an epiphany. And what I so that at the same time we were funded by Victor Durr and the Future Gen program. And so and here's a rendition of the Future Gen and the Future Gen 1.0, and then later there was the 2.0. But Victor Durr was the manager of the Future Gen project. And he says, Peter, where can we use your technology in Future Gen? And my immediate answer was compressor, CO2 compressor. These are CO2 compressors. Yeah, right. They're big. and they got a lot of coolers. Well, and the reason why they have intercoolers and so many of them, here's my friend up here at the top. The reason why I have so many intercoolers is that you cannot get very much pressure ratio per stage on an individual stage of compression on a CO2 application. Now, why is that? Because fundamentally, when you're designing a CO2 compressor, you cannot, or you design around a 0.9 Mach number at the inlet of the compressor. And so to do that with CO2, you have to slow it down. And when you slow it down, you end up with a pressure ratio of about 1.8 a stage or something to that effect. And so you get a lot of stages. The Ramgen technology did not have a Mach number limit. It wanted Mach number. And so it did not have this limitation. And we were talking about a pressure ratio of 10 instead of 2. So the compressor application became a 2-stage CO2 compressor for carbon capture instead of an 8-stage machine. And you can understand why the capital cost might be quite different. And also, you get a 400-degree discharge temperature off the stage that is quite useful in carbon capture, and you can recover the heat in the capture process or elsewhere in the power plant. So it was a pretty compelling story. And we ended up Dresser-Rand became an investor in the company. This is the Dresser-Rand test facility for the high pressure stage of the CO2 compressor. It's in Olean, New York. It's a 10 megawatt stage. I said, hey, look, if we're going to do this, we ought to do it at scale, because I was worried about getting stuck at the small scale and trying to control clearances and never being able to get to the large scale. So we built a 10 megawatt CO2 test loop, and it's a 10-to-1 pressure ratio with the discharge pressure up to 2,200 pounds or 100 bar, and it was a successful test. As you can well expect, this is a story that generated quite a bit of interest. And so what you see is these are in millions of thousands. So the activity was quite large, but you can see that it peaked around 2010 and 2011. And then it dropped down to, about half or a quarter of it in 2013. Well, why is that? We began to see the regulations that were going to give force carbon capture to be used on the coal plants, but not the natural gas plants. And as I started sensing this back in before these times, and I even wrote an article for Turbo Machinery magazine, and the title of it was "Passing Gas." And the question is, why are we not doing carbon capture on the gas plants? And the answer I kept getting from the various members was, well, we're going to do coal first. Okay, and so we never and then the regulations, the so-called new source performance standards began formalizing, and there was two versions of it. There was one that was set up in 2014, and it was done under the regulations, the Clean Air Act, and the new source performance standard was 214 and 15, and the levels were introduced in the power plan, and in that 2014 version applied universally to all power plants. Didn't matter what the fuel was. In 2015, they changed that under pressure from industry, and I'll tell you which industry, but the from pressure from industry to change it, and then they went to the power plant regulations specific to the type. And here's the war on coal that began in 2014, actually earlier than that. And what you see is the new source performance standard threshold on 14. You have the coal above the line, gas turbines below the line, and you can see carbon capture not required, carbon capture required. And so what you have the regulations written so it favors gas turbines, and this was reported in an article in a DOE, and you can see the capital cost dollars per kilowatt from with carbon capture and without carbon capture is substantial difference, and so the first cost is 5 times as much, and half the efficiency. Why do you? I mean, so nobody bought any coal plants with carbon capture. It would be stupid to do that. And no power company was pursuing trying to let's put carbon capture on the gas plants. So there was no interest in carbon capture at that time. And then there was complaints, and so they changed the ruling in 15 to a separate standard for each power plant. Unfortunately, carbon capture on gas was declared unproven. It's the same technology as on coal, but it was declared unproven on gas. And so then also the unabated combined cycle and unabated simple cycle were declared the best available control technology, backed. And there's another acronym that surfaces later. But it forced the coal plants to meet a natural gas level. Even in the 15 version, it was only 3 times the first cost and 3/4 of the efficiency. But this was the second phase of the war on coal. And natural gas exemption remains in effect today as we speak. Here's some of the data you can see. Here's the type of plants, simple cycle, natural gas combined cycle. There's a baseline report. Then there's the coal, pulverized coal, supercritical, ultra supercritical. And the standard applicable threshold, there was an interim level and then a final level. And what you can see is that a simple cycle gas turbine on natural gas does not have to meet carbon capture threshold. They meet it naturally. That's where that's how the regulations were set. They were set so that gas did not have the capture and coal did. 2015. Then we get to the conversation, we got all this conversation. We're going to cut emissions 32% by, 2030. The baseline, the starting point for the number is 2,416 tons per year in 2005. And so the baseline, the cuts attempted, here are the values. And what happens is that obviously start at the highest point. That's why 2005 was picked, so we can get the maximum reduction. But it was all done on the basis of coal. You can see that all of the changes were in the coal plant. The gas were fundamentally the same. Then we talked about the clean power plant and the clean power plant. Here's the 2004-16, and you had the 230 and the 240 forecast, high economic growth, reference case, and and then the oil and gas, high oil and gas reserves. But anyway, this gives you some measure of the reductions that we're trying to reach, but it doesn't really amount to much in terms of the real CO2 reductions in the clean power plant. It was a farce. Then there was an article written by Nature magazine, and they said, well, how much is this coal to gas shift really worth? And so they started to do a study on it, but you can see the coal to gas shift is this fuel mix thing, okay? And the contribution of the fuel mix, change in fuel mix, conclude the substitution gas for coal has had a relatively minor role in emissions reduction of the U.S. since 2007. Minimal. But the clean power plant is largely built on fuel switching. Then what happened is the renewable portfolio showed up in 2015. If you're not familiar with it, it's a state by state, and there's a percentage of renewables that they want to hit as a target. We have one in Massachusetts, and it's like 25 or 30% of your power must come from renewables. But what they don't talk about is that the renewables get to dispatch first. So if you make power renewable and you get to go, and the guy behind you, the power company's got to make up your variability, which we all know exists. And so they impose their inherent variability on the entire grid. And you get the duck curve. This is a duck curve that says, because we got these renewables here, and so what amounts to is that the gas turbine has to respond to the duck curve. And it's a pretty substantial portion, but now the duck curve is getting into be a canyon curve. Deeper, quicker, shorter. And what happens is that when you have renewables first in the dispatch order, you push the conventional back into dispatch order. The supply curve shifts with added wind. So what happens is you have an efficiency penalty, an emissions penalty. Your load factor goes from 85 to 65%. You got to deal with the ramp rates up and down, and you have the obligation to retain grid stability. Well, here's an interesting, in lieu of that, the forecast in 2024 is that is a relatively small amount of natural gas additions, but 80% are going to be simple cycle machines at 40% efficiency because they can respond quickly to the changes in load. Instead of a combined cycle at 60%, is hard to ship. Now, why is it hard to ship? Well, here's the natural gas heat recovery steam generator on the back of a combined cycle gas turbine. It is a big thing. And it's hard to imagine that being started and stopped rapidly, let alone putting a carbon capture system on the back of it. This came out this morning. I'll leave it in the slide deck, but the power plants, the combined cycle gas turbine power plants are getting more efficient. The heat rate's going down. They're getting better utilization, but still there is a problem because of the load factor. Okay, so now the topic of utilization comes up. Okay, how much do we use CO2? Let's go carbon capture utilization CO2. How much do we use? This was done by EPRI 2009. And here's the consumption of gas and liquid CO2, 100 million tons worldwide. So this is US. Okay, that is the equivalent of the largest 5 power plants. So the largest 5 coal-fired power plants are equivalent to the entire consumption of CO2 in the US. So what are we going to do with all this CO2? And so worldwide, this number is probably 800 worldwide instead of 200. So, but we have a mismatch, a big time mismatch between the CO2 we generate and the CO2 that we can use. So there's a whole effort to trying to figure out how we can make use of the CO2. Then at the same time, well, here's EOR, Enhanced Oil Recovery, very famous installation, Weyburn Midale. The power plant is located in North Dakota at the it used to be the Synfuels plant in North Dakota. They take the CO2 and they ship it up to Weyburn, and they use it in enhanced oil recovery, which is one of the fundamental uses of CO2. And what it does is it allows you to get more oil out of extend the life of the well, and so it's a pretty big deal, but it is sort of the prototype of this enhanced oil recovery that we were talking about, and that started in the year 2000. Then there's Sleipner. That's where Torre Tope from Norway Statoil was. And that was an injection well because they didn't want to pay emissions taxes in Norway. So they figured out how to put it underground in the North Sea. But that's where the experience comes on storing natural gas. And that was done in 2003. The enhanced oil recovery, you basically have an injection well, and it pushes some oil out with it. It's like using the soda water to clean a spot off your tie. It's a bit miscible, and so you end up coming up with a production well with oil, and you get a little what's called produced water with it, but the payback is a metric ton produces 3 barrels of oil. So you can see it's a good deal if the price of oil is high. If the price of oil falls down to $35, which it did, what happens to it in a case of Petronova, it shut it down. Okay, there's 3, when you talk about carbon capture, there's 3 plants that the world talks about. Sask Power, Boundary Dam in Canada. It was on lignite fuel. It is on Unit 3. It was a retrofit. It was this is a great picture of the size of the facility that we're talking about. It is not a trivial thing. This was on lignite. It was a mine mouth coal project, and they were able to work successfully using an amine process. But as I was told by one of the program managers, that even if it's the same mine, there is enough difference between seams within the mine that you can't account for the chemical changes. You have to modify. They could do it, but it was expensive to do it. So they basically gave up on it and turned into a natural gas combined cycle power plant. Then there's the other one, Petronova. Petronova is Houston. It was an after treatment to a coal power plant, Harris County coal plant, and they were adding it on the back end. It was they were going to did use the CO2 for enhanced oil recovery out in the Gulf of Mexico. Again, the scale. Here is the power plant. Here is the carbon capture absorber column. Here is the compressor system is somewhere in here. Here's the compressor. I showed you compressors before, so you get a sense of the scale. This is a big deal, and trying to put that on the back of a carbon capture plant is challenging. Then there's Kemper County, the third one that people talk about. This one was Sorry, let me go back one. Petronova was shut down for a while because the price of oil went to $35. It has now been restarted by Nippon, and Japanese company Nippon purchased it and are now beginning to use it again for enhanced oil recovery. Here's the Kemper County in Mississippi. Again, this was interesting observation. IGCC on very wet lignite. Again, a mine mouth system. It is a system that was Kemper County, Southern Company invested in this carbon capture technology because they were able to use it on this lignite. But if you can't ship wet lignite because it catches fire in the train car, I mean, you just can't ship it. So you have to use it where it was. It's a bit, I think it's a jobs program. It was a very complicated system and they did not complete it. They basically turned whatever assets they had back into a power plant, combined cycle natural gas power plant, unabated again, as usual, to rescue the investment. There's another paper. This is an interesting benchmark. This is a paper written by Timothy Grant. He's a DOE guy. I got to know him on we had intended to have a carbon capture conference in Boston. I had a couple of really notable people, but nobody signed up. This was in 2018. Nobody signed up in 19. But this was an interesting benchmark for an electric power plant. The capture costs roughly $60 a ton, transport 11, storage 33. These are good numbers, I think, to use to do any evaluation of CCS. Again, this is you have seen this before. I just wanted to reinforce. This is comes from Lawrence Livermore, and importantly, here's all of the energy that we buy, and here's how we use it. Goes through the Sankey diagram. Importantly, the rejected energy is 2/3. We waste or throw away 67% of the energy that we buy. Notably, the power generation of it is 35% efficiency because here are the inputs, here's the output. You do the math, it's 35% efficiency. The so-called hard to abate industrial efficiency emissions, they do pretty well at 51%, but these would be the industrial emissions, the hard to abate. And then you have the transportation sector, which, you know, the input output there is 21% efficiency on the transport sector. We've got a lot of work to do. One of the interesting slides I picked, it's process heat recovery. This is the hard to abate. This is in the 67%, that most of the heat is rejected at temperatures that are quite low, which is why it is hard to capture it. The only way to deal with this is using organic Rankine cycles to try to capture the waste heat. But about half of the process heat is below 200 degrees centigrade, which is why we waste a lot of it. Then we had the sort of COP 26-27. This is the IPCC, the worldwide climate sort of meetings, happens every year now. We had 26 was in Glasgow, 27 Egypt, 28 Dubai, going to be in Baku in 29. The takeaways, the Cliff Notes takeaways is one, we're not making the target. And so in order to square the circle, we have to capture these sort of, we have to create negative emissions to capture the overshoot. And that's a substantial amount. And so the strategy here is there's a couple of things. We have to build out the grid to accommodate the transition. And we're building out the grid with unabated gas-fired generation now, as we speak. And then we're going to do these hub initiatives. We're going to capture H2 and hydrogen hubs. But in order to make the hydrogen, we got to have an associated CO2 hub to pick up the carbon capture that's made or generated when you make hydrogen from natural gas. And then we have to rely on negative emissions to deal with the overshoot, and one of them is a direct air capture. And so what you're seeing is an underlying strategy of the natural gas industry to stay in the game by promoting hydrogen. And we have this Dubai. There was an issue at Dubai, the most recent COP, and the language calls for transition away from fossil fuels, and there was a big argument, and India complained because the original language was to eliminate, and so the agreement was to transition away, which means we're not going to get to it very well, and the sort of the phrase in it that I found interesting was just, orderly, and equitable manager. That's wiggle room in terms of how are we going to actually do it. Part of the deal was you have to have these nationally determined contribution. Each country has to put together a plan. And we're talking about transitional fuels. We're back to this bridge, natural gas as a bridge fuel again. It's just going worldwide. It was so successful in the US, it's going worldwide. The direct air capture is unproven, but the world has placed a lot of emphasis on it. This is from one of the IPC reports, and you talk about technologies under development. This is the contribution expected from that. That is direct air capture, among others. That's putting a lot of faith in something that doesn't really, so-called technologies under development. Okay, recently, April 2024, the DOE has finally reset their power plant standards. And so what they've done is create some new language. You have some on gas-fired combustion turbines, you have some baseload, high-capacity baseload machines, and there's a phase 1 and phase 2. The phase 1, we don't do anything. And the phase 2, we have to get 90% capture by 2032. There's intermediate turbines with the lower capacity factor, sort of wiggle room here, but it's basically a simple cycle turbine. And then you get the low load, real peakers, less than 20%, standards based on low emitting fuel, whatever that might be. And on coal-fired plants, you introduce terminology, long-term units. Are we going to keep these things, or are we going to delete them after a period of time? If you're going to keep them for a long time, you have to have operating beyond 2039. You have to have a plan, and 2032 you have to have the data. So there's the guidelines are basically not too difficult. Then we have these hubs that I mentioned earlier. This is a picture of the hydrogen hubs. Looks like I cut a Texas, but we're the Inflation Reduction, or one of the plans, is providing a lot of money to support the development of hydrogen hub, because we're going to use hydrogen instead of natural gas. We're going to put hydrogen in with the natural gas. We're going to mix it. We're going to try to use it, and maybe we'll even get to the point where our systems are entirely hydrogen. And the idea is you have a hydrogen hub. Here's a picture of one in Houston, and the idea is to have these hubs, and Houston's a good idea because it's got a lot of stuff there anyway. And so we're going to create a hub complex and a pipeline to sort of share amongst brethren and the like. And you can, I showed you Future Gen earlier. There was a Future Gen 1, which failed because of its complexity. And there was a Future Gen 2, which failed because of its complexity. We now have what I'll call Future Gen 3, 4, and 5, and the various methods of creating hydrogen from natural gas. Each one of these guys has this carbon capture on the back end of it. And that is why there's such an interest in carbon capture today, because it's behind the need to continue natural gas existence by turning natural gas into hydrogen, but we got to do something with the CO2. So we now have rediscovered carbon capture and storage that had been we saw it back in when the coal plants were being built, but now it's resurfaced in the form of to produce uh, blue hydrogen, as it is called. And so we have these hubs, and the hubs, CO2 hubs and the carbon capture hubs give us an opportunity. I like CO2 hubs. I think it makes sense. Not a fan of hydrogen hub, but I think CO2 hubs are definitely in our future, and it will be coming from uh, industrial processes and the like. So we're going to need hubs to collect it. Uh, there are other things that are feeding the hub. We're talking about geoengineering methods. You have the airborne stuff, and then you have the carbon dioxide removal, these sort of negative emissions. And here you see direct air capture. And you can see kind of here's direct air capture. And there's all sorts of various methods under discussion for negative emissions. And they were funded for the 45Q as credits for direct air capture. And what they've done is if you get $180 a ton for direct air capture if it's stored in saline, or 130 a ton if it's used for enhanced oil recovery. So there's a lot of subsidy to do direct air capture. The other thing they did is take it down into very small sizes. So some of these small scale plants can actually qualify. So the regulations are being set up to encourage and support direct air capture. Okay, well, there's two types of direct air capture. There's one, which is the solid or the dry type, and you have I'll call it a filter bed filled with some sort of coating that separates, attracts the CO2 in the exhaust, and then you have to remove it and separate it with heat, usually 200 degrees or so. And then there's the liquid process, which is, I think, is one that you can scale better. This is in effect, the same kind you would put on the back of a power plant, where you have a collector and then you have a shower head. It's a solution, and so there's the liquid type. These are renditions. This is a real picture of a direct air capture, carbon engineering, and this is sort of the array that you would get to experience if you did a whole slew of these things. That's solid. And then to have a real project, you have to do something like this. I see this every time I see this, I worry about the poor maintenance guy riding his bicycle around to figure out where in the hell all these things are leaking. And it's just mind-boggling that this would be a rendition. I do not see any utility support for this. I don't see a power plant. I don't see piping. I don't see compressors. I see fantasy. And you need 200 of these to do a gigaton. 200 of these things. Anyway, that's direct air capture. There are other versions of it by others. Similar concept here. Then you got this one that's got, haystacks I don't see piping, I don't see utilities, I don't see compressors. I see just interesting theory. This is the liquid process. This is an actual engineering drawing. I would note that they're trying to do they process 171 tons. The net capture is 112. Why? Because inside this loop, you have a combined cycle natural gas combined cycle gas turbine. Here, 60 megawatt combined cycle gas turbine, which produces its own CO2, which is then sent over here to the capture system. So, but you end up with 171 process net 112, and you need 1,000 of these plants to capture a gigaton. And then you have, what are you going to do with it? Well, I think it's like the hydrogen hub. We're going to take it here and capture it in these hubs and put it underground. And you know, I don't have a problem with this. I think this is where we're going to get to. The only issue is where's the CO2 coming from? And so that's a complete unknown to me. There are real life projects going on in Europe. There's a Rotterdam Porthos project. You can see a picture of it. The idea is to capture it from CO2 concentrations in the Rotterdam area and take it offshore and put it in the North Sea. They're using 3 of those big type compressors I showed you in the earlier slide. And then there's another area in the UK. Their strategy is to take these clusters and collect the CO2 in what they don't call hubs, but they are hubs, and take it out to the North Sea in carbon capture. These are the storage locations. To date, 27 direct capture plants, largely small size. There's the one Iceland that everybody talks about. These are all demonstrations. These are all experiments. These are not full-scale production. So it's an attempt to have it's an emerging industry, an attempt at it. This goes to the carbon dioxide removal costs. There's a bunch of technologies. Here's direct air capture and the cost per ton. The IPCC Review 6 estimate 100 to 300. Today prices 300 to 2,300. It's too expensive in terms of capital costs, and these are notional attempts. You have all sorts of other types. These are chemical and agricultural and things like that that people are working on and their relative costs. One of them recently, today, May 1st, 2024, Frontier signed a deal with Vaulted Deep. These are names I don't know. Frontier is a commercial negotiating platform, and Vaulted Deep is the person who puts it underground, and they were putting it underground at $421 a ton, if you can believe the numbers. 58.3 million and this many tons. That's a lot of money compared to the chart that I had showed you. But there's also this carbon dioxide removal leaderboard where you can buy and sell credits. Here's the Frontier buyer, and here's the Vaulted Deep. Here's the same numbers, but you know, we're talking about relatively small quantities at this point in time. Another tell. Here is a Carbon Capture Technology Expo in June, this month coming up. And here's the conference agenda. This is the tell. Here is the conference. And over here you see carbon capture, utilization, storage, and blue hydrogen. And then you see the agenda. Co-located with the hydrogen technology We're talking about the combination of CCS and hydrogen, application to hydrobate, CCS and hydrogen, build a business model for CCS, and so it is about hydrogen. It is about so carbon capture and sequestration in the discussion as we speak has two roles. One is the production of hydrogen to keep the gas industry alive, because they're basically looking at it as a way to continue their existence. It will make hydrogen out of methane. And the other is developing a utilization industry of CO2. I think there's a mismatch there. The big challenge, can you make it back into fuel? And it's an energy problem to do that. And so storage is in our future, and the hubs for CO2 are a good idea because it builds out the infrastructure and the pipeline. It's just, where does the CO2 come from? And so that's essentially what's going on carbon capture. I'll open it up to questions at this point.
Well, thank you. Thank you, Pete, for a not only comprehensive, but absolutely mind-spinning
Yes, I hope
presentation.
so.
Well, the interesting thing from my perspective is it just seems to me that there are so many different initiatives and so many different potential approaches that I wonder, it reminds me of an experiment in what is, for example, drug manufacturers use something called combinatorial chemistry or combinatorial
Yep.
synthesis. In other words, you've got this massive number of possible solutions to a problem. And then you whittle them down somehow until you reach the point where you've got a couple that may be promising and meet your objectives. Is anyone trying to apply something like this to the massive number of approaches that are being proposed to deal with carbon and carbon dioxide?
I think you should apply it to how do we turn carbon back into a fuel. Okay, that
Yeah.
would be good. And then how do we find better ways to use it, create new material? But the chemistry is the chemistry. I'm not a chemical guy, but
Yeah. And, well, I'm not suggesting
there's a
that the chemical.
scale. There's a scale problem. We
It is a
produce so
scale
much.
problem. And let me be more clear on what I'm thinking. I'm very interested in what's called computational material science and engineering.
Yeah.
And the objective is to say, we need a new material for a new engineering system. So,
Yep.
for example, a hypersonic vehicle is going to require new materials that don't exist today.
Mhm.
And so you go into a laboratory and you come up with you develop a model for how to develop, how to engineer such a material. And that could include the chemistry of the material, the structure of the material, its availability. All of this goes into this combinatorial synthesis approach. And you wind up with a huge number of possible combinations that could work. The analog being all of the combinations that are available for carbon removal. And then you say, all right, how do I limit that to a number of technologies that may be workable and are practical and tractable? And that's the kind of approach I wonder if there's anyone thinking in those directions. You know, I I guess I'm overwhelmed by the number of avenues that are seemingly available throughout the planet to deal with this problem. And yet I don't see any one of them really reaching out and saying and being the center of focus. Or am I missing it? What is your focus? Where do you think you should put your money if you were going to invest in carbon removal? Where would you go?
I would not go in direct air capture, because direct air capture is starting to try to take it out of the atmosphere is
Yeah.
stupid. It's under, but I think that the utilization of carbon is where it could be applied. How do we take CO2 and use it to help minimize the scale mismatch that we have? can we make it into a fuel? The only application that is of the same scale is fuel, and fuel is an energetic loss in terms of turn it back into fuel, and some of the chemists in the crowd can speak to that. So,
Yeah.
but there is an attempt to turn it into sustainable aviation fuel, if you will. But there's a subsidy to do that. So it's a kind of a false, but it's a fuel. How do we turn it into a fuel? But when you run out of that, you end up, what's the best way to store it? And then the other question is, should we be making hydrogen at all? And why? Because the interest today in carbon capture is based on hydrogen.
Yeah. Yeah. Well, let's take some questions. I have a couple more, but I see hands up. So Eddie, let's go to Eddie.
Yes, speaking from a physics point of view, and if you have to use basically carbon-based power production in order to even convert CO2 from from a power source that's essentially carbon-based, it seems like it's an impossible efficiency problem.
It is.
And so unless you power them by green energy, I don't see how you can even make the argument from even you know from the basis of cleaning up CO2. You get to burn that fuel as well.
Albert?
Yeah, hi. First question is, what happened to the RAM pressor?
Okay, the RAM pressure, yeah, I thought that might come up. The RAM pressure, the Ramgen was sold to Dresser-Rand. They bought out their share, our shares, and so we became it became owned by Dresser-Rand. I left the company at that time. I didn't want to do that game, and then shortly thereafter, Dresser-Rand was acquired by Siemens, and Siemens has a full cadre of compressors. And so we completed the development of the low pressure matching stage to match it to the high pressure stage, but it never went beyond that because Siemens had existing technology. I do see this cutaway of Siemens, their barrel machine, and I see a couple of front ends on this thing that are let's see, from the current slide. I see a couple of front end shapes that look suspiciously like the Ramgen technology. It's on hydrogen, so the Mach number is low, and so you may be more challenged. This is more likely to be a high specific speed mixed flow machine, but this looked suspiciously like we developed. But aside from that, I can't tell you what happened within Siemens, other than to my understanding, it's on the shelf.
But my question is fundamentally, was it abandoned because other technology already existed, they were invested in that, or whether from an efficiency point of view, it was not as good as what's available?
The bottom line is that at the scale, with two stages, we were a little shy on efficiency, and the control range was challenging. And those problems could have been worked on, I think, and resolved. But and then you have to combine that with the fact that Siemens owns their own technology. These are
Okay, clear enough. Now, my next question is, I agree fully with you about the craziness of trying to do direct air capture.
Yep.
I can't understand is why so much money is putting in that, and and the capturing it from, let's say, single stage gas turbine is not being looked at. You would still think that regardless of the efficiency of the turbine, it's easier to capture it from 10% CO2 than 0.04%.
Yes, yes. Well, again, the regulations initially by EPA were never resolved. The 2014 made coal plants. I mean, it never the carbon capture applied on a gas plant was declared unproven, and then it was lost in this best efficiencies BESR. And so it was lost in the regulations. There was no forcing function and there's no price on CO2. So there was no driver to consider it.
It's sad that it slipped. I mean, yes, perhaps so then, but now one should revive that as opposed to going with direct capture.
Well, yeah. Well, the problem is today the capturing it at the power plant is really we're using batteries to do the peakers, and the load factors are low, and nobody wants to spend the capital to do all this fancy stuff on a machine that's only going to have a load factor as a peaker. And you see that in what the forecast was. This one here is this one, where the forecast for planned capture, minimum number of gas turbines, the lowest percentage of gas turbines, 25 years. And the ones they're buying are simple cycle because they're going to be peakers and you can't cover the capital. And the regulations allow them to do that. The regulations make it okay. And so there's a convergence of a shared interest.
Thank you.
Can I say something, Pete?
Go ahead, Harry.
I'm sorry, I don't know how to push the button to raise my hand.
Okay. Go ahead.
I guess there's a couple of things. You folks who live in Massachusetts are not too far from Bellingham, Massachusetts,
Yep.
where in 1990, they built a combined cycle plant with partial carbon capture, and they used the CO2 in bottling 7-Up down the road.
Yeah.
It turns out that the EPA ignored that existence of that plant until these new regulations came out. And when you read the EPA documents that are published, they mention Bellingham combined cycle plant as having proven that carbon capture on gas turbines work. That's why they could justify, along with Petronova, they could justify pushing carbon capture on existing and new power plants. The thought I'm having is that when you talk about peakers, I mean, think about the percentage of coal that now, the percentage of our electric power in the US that comes from coal in the past, say, 10, 15 years. So since the clean power thing came around in 2015, like 10 years, coal has gone from nearly 50% of our generation to about 25%. It's been replaced by renewables and gas. And in fact, I think the US displays the greatest reduction in CO2 emissions from power generation. And you can't really expect, first of all, if you put a carbon capture unit on a peaking plant, it's probably the biggest waste of money you could imagine because the plant will run for a few hours a day. And I think they recognize that by saying if you run it for, as a peaker, you don't have to do anything except use clean fuel.
Right.
Other thing I was going to say that hydrogen for power generation is another big mistake because right now, the numbers that I've seen in some article I worked on was that if you took all the curtailed wind power and solar power in the United States, curtailed, meaning excess or shut down because it wasn't needed, and use that to electrolyze water and make carbon-free hydrogen, you might run one large combined cycle plant at base load continuous. In other words, the amount of solar and wind that has to be built just to make enough hydrogen to run one power plant, it makes no sense at all. I mean, the inefficiency of electrolysis is incredible, and the use of, like you say, the use of natural gas to make hydrogen, you create more CO2 from the conversion of natural gas to CO2, I mean to hydrogen, than you do if the plant just ran on natural gas directly. Taking the gas and converting it to hydrogen creates more CO2 than if you just burned it in the combined cycle plant in the first place.
But that's
some
why
of these things-
the gas industry is interested in blue hydrogen.
I mean, the whole thing is ludicrous. And you talk about the myriad of solutions. You look at the numbers that Pete puts up with the curve showing where we are today and where you have to go with negative emissions to actually meet the targets that are being set up by these international, by the UN, the COP. It's almost, no matter what you come up with, you're probably never going to get there. And, most of us, let's say all of us, will never see any real attempt to get close or a measure to get close. And maybe by the time the next generation comes around, and I know this is heresy, but maybe they'll find out that reducing CO2 from the atmosphere by man's attempt to fool around with Mother Nature and all, isn't what's causing the Earth to warm up anyway. But that's in the history. That's the part of your story, Pete.
One of the secrets is China. Of course, China uses half the world's coal, and they seem to have an ability to get things done. I expect they'll come up with something at some reasonable point that'll mitigate to some extent, and then they can force people to use it. Not like us, where we got to get a voluntary contribution.
Well, we have you say you have the natural gas industry, you have the gas turbine industry.
Yeah.
I mean, one of let's put it this way, one of Westinghouse's main competitors in the power generation business, the #1 company, probably has the strongest lobbying business in Washington you could imagine. I mean, I've personally seen things that they've accomplished by having a plan what they want and knowing who to work with in Congress. It's unbelievable what you could stop and what you could push and all that kind of stuff. So anyway, it's a lot of good stuff in it, and a lot of good history. Thanks, Pete.
Pete, I have a sort of a wild-eyed thought here, and I want to get your reaction to it. If I look at this from 30,000 feet, or maybe I should say 329,000 miles, like from the moon, and I look at the Earth, and I wonder about what our problem and how to deal with it. I start thinking of thoughts like the following. We know there is a supply of CO2 on this planet. There are sources of all kinds, from combustion engines to etc. There are sources of CO2. There is a demand for CO2 in terms of natural photosynthesis, and there is a demand from the point of view of man's use of carbon dioxide and carbonation of beverages and so on. So there's a demand, there's a supply and a demand, but the balance is what's troublesome, isn't it? It's what's left over.
Yeah, it's the balance and also the speed. You could argue planting trees, but there's a speed thing that has to.
Well, let me continue. What my concern is, having heard what you described eloquently in terms of all of the permutations of approaches that are being considered for managing our carbon excess, our carbon dioxide excess, there has to be I think there needs to be some kind of focus. And, my initial comment about combinatorial approaches was a thought in that direction, is to provide some sort of focus. But I have another suggestion. What if the world were to say, there's an ideal approach to managing carbon dioxide, or we'd like to suggest there should be an ideal approach. And that approach would be, first of all, to remove carbon dioxide, and at the same time, in removing it, to produce electricity, and to take the products of that, the generation of electricity, and use them somehow in some other natural corporate industrial sense. So you recognize there's carbon dioxide. So you say, I'm gonna capture that carbon dioxide. I'm going to use it somehow to produce electricity, and I'm going to take the products of all of this and I'm going to use them in industrial.
Thermodynamics is going to get in your way.
I mean,
Michael,
no.
Michael.
I know.
Chemistry.
No. But here's the point.
Physics.
I know this is blue-eyed and wild-eyed and so on.
It is.
The point is, there are approaches to do this. And we have one of the guys. Where is Michael? Where is Michael?
He got his hand raised.
I'm here.
Oh, Michael has a technology. Well, I should let Michael explain it, but let me just capture this. I'm not sure this is the only way to do it, but if you look at biomass, that's one source. There are many sources of carbon we have to deal with. Biomass is one of them. Michael can convert biomass to carbonaceous products that can be used, for example, introduced into cement.
Yeah, no, I understand all that.
And his process
still a problem.
But wait, just a moment. But his processing also generates electricity. So here's the technology. If you look at just that one source and you say, this meets all my objectives, therefore we ought to put a whole lot of effort into doing this. Then we look at, well, what are other sources? Carbon dioxide produced by consumption and use of fossil fuels. Let's figure out how to go through the same process. But I just think we need some sort of global focus. That's why I'm looking at it from the moon, because we don't have a global focus right now. It seems there are a lot of initiatives and a lot of regulations, and they're almost counterproductive. Now, maybe I'm really way off base, but I think we need some kind of focus, and I didn't see it, or am I missing it, Pete?
There is no consensus. The focus is the IPCC.
And what does that lead us to?
Intergovernmental Panel on Climate Change. They're the ones that are producing all these reports and this stuff. So I mean, and they are the focus. That's where we have this defined national contributions.
But they don't seem to be.
Well,
I don't see focus coming out of that, Pete.
You've agreed to transition away, though.
Yeah, go ahead. I'm sorry.
Because you have equity. For equity, you have to have India able to develop into a major economy, and they have all the coal, so much coal, and they have very little gas. And
yeah,
for equity, you have to have a country like India, which is the most popular, populous in the world. To burn their coal first, and then they could worry about cleaning up the earth.
well, I'm just really, I guess I'm really concerned that I see a lot of effort being placed by nations all over the planet, but without some central focus, I don't see a solution emerging. And I see hands up. Let me stop talking. Let's go to Michael, and then we'll go to John and Eddie. Michael?
Yeah, I was just going to say quickly, there's a lot of players in this game now. It's still the wild, wild west, and you've got snake oil sellers, and you've got people that are legit. You've got outright liars, and you have very serious people. So I think a lot of the, as you say, Ron, the lack of focus is there's so many inputs trying to create the conversation. My own feeling is, because I'm in biomass, is that we can take waste biomass, which could include seaweed. There's massive amounts of that. The ocean is covering 3/4 of the earth. We can convert that into pure carbon and biogases, which could also be used to power vehicles as well. And we can make money at it. And I'm kind of looking at all of these other processes. It costs $2,000 a ton for direct air capture, or $600 a ton for this or that. We can make money sequestering CO2. And it's very easy to determine how much we're sequestering. And in fact, much of the current day investment is going towards biomass-based systems, biochar systems.
Like these,
Excuse me, sir?
like this one. This is basically one slide among the many. This
Yeah.
is,
Well, I mean, but here's the thought, though. I mean, if you were to take the position, if you were to take the position that there are various sources, biomass is just one source. There are various sources of carbon dioxide, but if your operational mode was to say we're going to take whatever this source is, and we're going to take that carbon dioxide, just as Michael takes his biomass, he creates carbon as a reaction product, but he produces electricity and at the same time removes the carbon dioxide, the biomass. If every one of the technologies that are given some stamp of merit were to take the approach that they have to look at it from that perspective, wouldn't that be a means of focusing the effort?
this is not a new conversation. This is a McKinsey cost curve dating back to 2009 that shows the various actions you can take.
Peter,
Yeah.
we stopped the sharing of your screen, so I have a feeling you're trying to show us a slide, but we're not seeing it unless you go to screen share again.
Okay, screen share. Okay, that's it there, right?
Yeah.
Okay, but I have another slide deck here. This was done by McKinsey in 2009. And this gives you the sort of a recipe for things that you can do in the form of mitigation.
Yeah.
These are things that save money, and these are things that cost money above the line. And the width is the amount of energy of the CO2 that it saves. And it covers just about all the things you could do until even.
But I mean, wouldn't it be useful if there's some way of saying, well, we could do that, but it's not going to meet our goal. Let's remove it. So that there's some kind of focus. I'm hung up on this. I apologize for that, but I really am.
There's not one answer. That's the problem.
Yeah, I know
there is not one answer.
Yeah.
And there never will be one answer. These are, and these conversations, they date back to Princeton's work in the year 2000 or before.
Yeah.
Wedges. These are wedges in a different arrangement, but it's not one size fits all. You got to do all of the above.
So where do you think we're headed, though, Pete? I mean, where does this?
We're headed for some more disasters.
Yes, that's true.
Well, that's not a good conclusion.
No, it is not.
I know.
But you asked me where we're headed. That's kind of where I think we're headed.
In long term, you're talking about a reduction in population. The curve of CO2 in the atmosphere and the number of humans on Earth is amazingly correlates.
Yes.
And just man creates CO2, and we're heading for 9 billion people. And there is predictions about how we're going to peak the population somewhere along the way, because there are places like Japan that's already losing population. And I think didn't you wrote something about that in one of the articles? I think it's
yeah.
Long term
price on CO2.
Yeah.
I always say in the long term the planet's going to win. The planet's not going to have a problem in long term. We're talking about billions of years of going through all this kind of thing. So man is
got a couple of hands up, Eddie.
Yeah, Eddie, and then Avi.
Yeah, I'm gonna basically make a simple statement that with current technology, we just can't get anywhere. And the only hope we really have is the evolving technologies that are carbon-free and provide massive amounts of energy. I kind of am hopeful that in fact that might occur, because I'm seeing signs at least of nuclear fusion and advanced geothermal, for example, coming along. And it's power that will get us out of the mess.
Yep.
Because then we can do other things. And there's also, by the way, other ways of producing hydrogen, which do not involve electrolysis, but involve catalysts. And I believe those are coming along as well. So I'm kind of not all gloom, but I think we're going to go through a heck of a time, and my poor granddaughter is going to have a heck of a time in 20 years, far more than we are experiencing today.
Avi?
I'm naive with this subject, but it occurs to me to ask, is there any way of using the organic principles? I mean, we know that through photosynthesis, that plants convert carbon dioxide, excuse me, into oxygen. And is there a way of doing this on some kind of very grand scale so that after you capture carbon, or even if it's uncaptured, this could be used as a way to at least approach the problem. I think there really does have to be multiple approaches to find out which one works or which ones work. But I don't know if something like that would provide any kind of assistance to the problem.
Michael, you want to comment on that one?
Well, I think we're kind of doing that in partnership with plants. We're relying on their photosynthesis, and there's certainly folks out there that are working on artificial photosynthesis. But photosynthesis in itself is only 6% efficient. And I'm just not sure we're going to come up with something artificially. But again, what we're doing in the biomass world, in biochar, is we're converting that absorbed CO2, carbon, into solid elemental carbon and permanently sequestering it, but also using it to replenish land, revitalize depleted soils to produce more plants, which absorb more CO2. We can decarbonize concrete. We can build highways using natural carbon that we've sequestered. So I think that's the closest we're going to get to that, Eddie.
On Sunday night, 60 Minutes, they had a segment on reforesting the Amazon.
Well, you know, forests are rapidly in some areas becoming net carbon emitters. So in Canada now, the forest fires last year, between the second week of May and the last week of June, they emitted 1 billion tons of CO2, which was more than the entire country of Canada does in a year. Plus, you had all of the pollution on top of that, which created enormous amounts of sickness. And if you look at the wildfires in California and Oregon and Washington, and especially Australia, it's the same story. Planting trees is not necessarily going to reduce CO2. There's some real questions coming up about that.
Interesting.
My daughter, by the way, in Calgary, I was going to go up there in the summer, and she warned me not to go up because it's so bad now, the air pollution in Calgary during the summer, that she hardly even goes out of doors anymore.
Some of my
That's the
friends wear
situation
masks
there.
in their homes.
Yeah.
Yeah.
Pete, you know, we've reached the witching hour here. It's I promised every speaker that we'll end by noon. We're a little bit over, but I want to thank you profusely for this presentation. Sometimes I think we on this planet need to be shocked into reality, and I think you've certainly done that to yours truly, because I you know, not only in terms of the massive amount of effort that's being put into it, but your ultimate prediction that we're headed towards a calamity, I think, is frightening. And I don't think the general public takes this all that seriously. I think there's a problem that we have in this country. It's a combination of public will and political will and technological will. And right now we have not mustered, as a population, we have not mustered the intellectual strength to bring them together. I wish there's some way, Pete, that you could you could speak on this issue to people who will listen. We are listening, but we're not enough. We've
I'm
got
frustrated. Okay, that's why Harry and I have these conversations. Harry is my voice. That's true. You are my voice.
Yeah. Well, there's a massive issue, and I think we're spinning our wheels, frankly.
Yeah.
And it's
Well,
really
the economics aren't, there's no forcing function. There's
yeah,
no price on carbon. There's no penalty you pay in the near term. And we have this news cycle that, we're talking about minutes here now, but these are 100-year impacts, and the two never meet. And
yeah.
so we don't connect A and B.
Well, as always, I think our question and answer session after a presentation is always, for me, incredibly informative.
Yeah.
And this is no exception. In
Yeah.
fact, this may be the pinnacle, because I think this is really important. I just wish more people had heard it. I wish more people would take notice, and I wish we'd have some serious leadership among in our legislative and congressional bodies to deal with it. But technologically, we've got a role to play too. We've got to help narrow down the possibilities, because they're just it's mind-boggling, the different modes of philosophy that have taken root in terms of carbon dioxide.
Well, I'll make the slide deck available to you. You can distribute it as you wish.
I would love to do that. Thank you. Let's do that.
I think also,
I wish we could end on a happy note. We got to find something good to talk about here. I don't know. But I'm delighted, Harry. I'm delighted to see you here today. Come back again. Energy and environmental issues have been a focal point for the forum this year, and I think Pete has added a perspective that's really, really incredibly important. So I hope I'm on the Cape. I'm going to have a good weekend no matter what. But this adds another dimension to my thinking for the weekend, Pete.
Okay.
Can I close
All
on one thing that'll make you feel
Thank you,
happy?
Pete.
Yeah.
I'm trying to help somebody sell some gas turbines in Ecuador,
Yeah.
where they have no money, they have no hydroelectric power because of the drought. I'm talking to people at the Export-Import
Oh,
Bank.
yeah.
I found out yesterday that Export-Import Bank won't lend money to export for projects in Ecuador where there's no electricity, because unless you burn natural gas, won't lend you money if you're only going to burn oil. So it's the funniest thing. Here's a poor country in the dark, and you have the heroes in Washington saying, well, you can stay in the dark as far as we're concerned, because you're going to add CO2 to the atmosphere. And yet 90% of the energy, the electricity in Ecuador normally comes from hydroelectricity. Here they just need something to run for a few months, and we can't find the loan guarantees from Washington that we need.
Yeah.
There's a little political problem in Ecuador.
Yes, I think that's
Well, they
probably
have a new president who
Yeah.
promised to do the right thing.
I was down there a few years ago, and the climate has changed, and their dry season turned into a wet season. And then their wet season turned into a dry season.
The lights go out during the dry season because they don't invest in what they need to keep the lights.
Well, it gets worse because they have avalanches in the mountains. We actually had to be delayed.
Let's find some
But
good
anyway,
news.
that's other stuff. Sorry.
I want to thank you all. This has been a really wonderful conversation.
Thank you for inviting me, Pete.
Okay,
Take care.
my pleasure.
Have a good
Bye-bye.
weekend, everyone.
Okay.
Peter.
Take care. Thanks, Pete.